the back end of the compiler. So we're here on the last portion of the back end of the compiler where we're generating actually assembly code. I hope you're making some progress on the arrays and pointers. But first, let me ask any questions about generating code for arrays and pointers? Yeah?
I was wondering if we could go over the homework answers.
Oh, right. Homework answers. Yeah, good idea, because that is covering that same content. Okay, so the homework was asking about two operations. One was assigning a variable to some constant, and the other was assigning x to a dereferenced variable. So the reason I asked both of these is that at the assembly level, both of these kind of look like pointer operations, because at the end of the day, these variables are really just placeholders for some memory address in RAM. At least, yeah, typically variables are backed by RAM, and so all of these are actually effectively pointers because they're memory addresses. And so I just wanted to illustrate the difference between accessing the value of a variable versus accessing a dereferenced variable. Okay, so let's go over the first one. So first of all, what does this mean to have an offset from RBP? Or why is that relevant to our compiler backend? Yeah.
It means that y is 8 bytes
From the base pointer, yeah, exactly right. And so what was the base pointer? What was the base pointer for? Exactly, yeah, it's a stack frame. It points to the stack frame. Okay, so in order to, let me get notes open here. So what this is saying is that we've got a stack frame for whatever function we happen to be in. And our stack frame has an address that's held in the base pointer, and an offset of -8 from that address. We've allocated space for the local variable y. So in Intel assembly, what does the instruction look like in order to read and write values from an offset from RBP? How do we access? So what's the instruction that will move data, I guess, first of all? Move, yeah, good. So this is going to be some move instruction, and yeah, you had an answer about how to access the offset.
Yes, it's the offset followed by the base pointer parentheses.
Okay, so we've got, in AT&T syntax, we have the offset followed by the base pointer register in parentheses. And what this means, what this instruction maps to, is take the address that's in the register given. The parentheses say, don't give me the data of that address, or don't write to the data of that, don't give me the data from that register, don't write to that register. Instead, read or write the memory address that that register holds. So if RBP is pointing here to our stack frame, which is some location in memory, some address, then the parentheses say read and write that address that the register holds. And so if you can wrap your head around this, then you'll have the basis for understanding pointers in C and why they work the way they do and how they work at the machine level. And even if pointers are still confusing, you can at least go back to kind of first principles and work out what's happening in pointer manipulating code. So that's exactly right. So this is how we access the memory address of y if y is a local variable that has some address on our stack frame. Okay, so y equals 3. we're assigning 3 to y. And in C-like imperative languages, that means we're setting the memory address associated with y to the value 3. We've got our memory address, our operand here that will access the memory address associated with y. So all we need to do now is to craft an instruction that will move the immediate value 3 into that address. So how can we finish this? So I guess first of all, in AT&T syntax, which operand is the destination register, or destination address register, yeah. The right operand. So AT&T syntax, a little confusing compared to Intel syntax. The second argument is always the destination register, and the first is the source. And so in AT&T syntax, how do we specify an immediate value? So you have our constant. Yeah, did you have an answer? The dollar sign, good, yeah. So the $3 in AT&T syntax. And so this is our instruction. Move immediate value of 3 into the address associated with y. And for function local variables, the stack frame is where we store those values. And in the AT&T syntax, we use, or in the Intel architecture, we use this memory indirect addressing in order to get to a memory location. So, I mean, you could also just put in, you could have a literal memory address here as well that you could move into. But because we don't know at runtime where the stack frame will live in memory, instead we keep this address of the base pointer of the stack frame in the RBP register. And then this is the, in AT&T syntax, this is how you say, give me the memory location that's held in RBP, held in the register. So RBP itself is a pointer. So this register, you can think of it as a pointer because it holds a memory address, and the way we use it is to determine the destination for a memory store. Questions on this? Questions on this? So this for constant values, yeah. So this is how you would do move y equals 3. In our compiler, if you follow my scheme, this instruction will be compiled in 2 steps. First, you'll have the evaluation of expression. So you could certainly generate this code in our compiler, but the simpler scheme that I gave you was to generate code just for the constant first. And the way this would look in our generated code would be to use some temporary register. I always recommend using RAX as a simple scheme. And then every expression ends with push. If you remember, we talked about that convention last time to allow multiple expressions to store their temporary variables. And so this would be the code to generated from just 3. And then the code generated for y equals some expression would be to pop our code. Test. Okay. Sorry, so our code to generate y equals would the compiler would first figure out what the destination address would be, or what the memory indirect offset would be for it. And in order to get the child expression, 3, it wouldn't matter what is on the right-hand side of the expression. If you use our convention, you can always just pop whatever's on top of the stack. That will always be the last thing on the stack. And then instead of move 3, we would move whatever the right-hand side is to whatever offset from RBP we had from looking up in our symbol table. Questions? Questions on this? Okay, so let's look at problem 2. So that was problem 1. So notice that RBP acts like a pointer, and even though we're in our language, we're not using a pointer, in order to access the memory of y, we are using RBP as a pointer. It's effectively an array of local variables. So to make this confusing, how do we deal with a variable, which is already a memory address? How do we deal with a variable that's being dereferenced? Okay, and so I said x has offset 8, and y has offset 8, and x has offset negative 16. So let's draw our stack here. Here is RBP. Here's the memory address for y. Here's the memory address for x. And they have these offsets, negative 8 and negative 16. So just as a little reference here, how do we reference the memory for 8, or for y? It's just like before. And for x, we use the same memory indirect addressing as before. So negative 8, parentheses, percent RBP. So okay, so in the compiler, this will work the same way, where our goal is to first evaluate the right-hand side. And so, okay, so what do we need to do in order to get the value of whatever y is pointing to? Yeah.
So you can move it into another register for us to use that value.
Okay, so what your fellow student said is to first get the value of y and store it in some temporary register. Okay, so let's do that first and see where this is going. So we use a move instruction that takes whatever the value of y is, just like we went over in the last problem, and let's just store it in some temporary register. Now, in the back end of the compiler, we could push this onto the stack to hold on to it. But for this assignment, let's just go through one simple translation of this code. So now we have RAX. So RAX, okay, so what does RAX contain right now? Or is there, what in memory is the same as RAX at this point? Yeah. Not quite. So let's say y is 0x e7. After I do move negative 8 from the RBP into RAX, what value does RAX hold right now? Yeah. Which is? Right, 0x e7. So I know I went over an example last time, maybe overly clever example, where we had the address of x and y, but it's in this this is really off the edge of the screen. In this example, we actually don't know. I didn't give any information about what y's value is. But whatever it is, it's stored in this memory location, this offset from the base pointer. And so just as an example, if it happens to be 0xe7, after this move instruction, this 0xe7 is going to be in RAX. So this is the value of y. Just like in C, when you deal with pointers, the value of y is some memory address. You can't really see what it is when you're working in C. It's just abstracted away into a symbol. But now RAX holds the value of y. Okay, so then how do we dereference y? How do we get the value of whatever y is pointing to? Or what AT&T syntax can we use? Yeah.
You put parentheses around it to do it.
Okay, you put parentheses around it, and what do we put parentheses around? Good, RAX. So RAX holds the value of y, and if we want to access the memory location that y is pointing to, we use this memory indirect addressing, just like we did with RBP. So this is the essence of what pointers are in C. Y is just like any other value. It's holding some bits, some integer. But whenever we do a dereference or any other pointer operation, we use a different opcode in the machine in order to access the memory that's pointing to it. So instead of operating on the value of y, RAX, instead we operate on the address that RAX points to. It's good. So this is how we access the value on the right-hand side of this assignment here. Okay, so now let's evaluate x equals whatever the right-hand side is. So how do we move some data into x? And I'll just let's just think of this problem separately. So how do we do x equals some value? Yeah. Move whatever the value is to.
And then we would do -16 since that's an offset, and then parentheses.
Right. Whatever offset from in the stack frame x is contained in. So this is how you access x. So whatever value you had you wanted to store into x, you would store into -16 offset from RBP. Okay, so connecting these pieces here, so this was a translation of star y, or actually this was, more correctly, this was a translation of y, and this is how you access star y. How can we put these pieces together? So how do we what do we fill in this box in order to store whatever star y is into x? Yeah, exactly. So this is how we access star y. So in order to implement x equals star y, we use this memory indirect addressing of RAX, which RAX holds y's value, in order to get this memory location. Now, I think in the Intel architecture, you can't actually move between memory addresses. You need an intermediate register. So in order to make this actually working assembly, we would have to first use some intermediate register here. So RAX is already being used, so I'm going to use RBX as another temporary, and then move that, whatever is in RBX to X. But it's the same thing. We're just using a register to hold that value. Yeah?
So for our simple C project, would we expect it to do that, or with the intermediary, or would you be able to just use the dereference?
So you could just use, you'll have to use a temporary register no matter what. I think Intel does not support it. So if you use the scheme that I lay out, let me go over that, where you always use the stack to hold intermediate values. Let's take a look at what that would look like. So it's a little more complicated because we have this nested assignment. Let's do it this way. So we have an assignment here. Let's see how to break this down. let's say this is our assignment, and it's being assigned to a dereference, and that dereference has the star operator and y as the right-hand side. So the way we would do this if we wanted a simple, naive way to do this, where we only have to focus on translating each of these nodes one at a time, when we translate y, we don't know at this point, when we're going to generate assembly code for y, we don't know that it's going to be used as a dereference or an assignment. If we want to make this simple, we can just generate code just for this ident expression in our language. So to generate code for the ident expression, we just take, you look up in the symbol table whatever its offset is, and this is how you get the code. This is how you get the memory address for y. And so all you need to do in ident expression, I think this is given, is to just push it onto the stack, and that will ensure whatever its parent expression is has access to that value. And it also means that when you're translating ident expression, you don't have to care where it's being used. You can just follow this convention so that all of the expressions will be able to access their operands without knowing what kind of expression it is. So this is the code that you would generate using this recommended scheme to generate just y here. So that would be just y. And then when we go to generate the code for the dereference, we don't really have to care how this address came about. There could be some complicated pointer arithmetic, there could be two dereferences, there could be anything here. And in C, that's more or less the way it works. You can dereference things that have already been dereferenced. You can do multiple pointer dereferences at a time. Or I think you can even do arithmetic inside of the parentheses and then dereference that, if that's allowed. So that's all you need to do for ident expression. And then when we get to this dereference, we just take whatever was given to us in the top of the stack by the child expression and just pop it off into RAX. And I know this looks, when you look at the assembly code, this looks like what's the point of doing this? This is obviously inefficient. But it makes compilation much, much easier. And don't worry if you want to see how compilers actually resolve this. The compiler will not. Compilers will actually generate this kind of bad code effectively. Instead, they use later optimization phases to make it faster after the fact. And you can take my graduate compilers course next year if you're really interested to see how that works. But don't worry right now about performance. Correctness first, and then performance. Yeah.
Could you simply push negative
Yeah, you could probably do that too. Yeah, if you want to make it a little faster. I'm concerned with correctness and make it very. Actually, I don't know if you can because it's a memory address. I don't know if it'll do that move. It may not actually. You may have to push a register. I'm not sure. Okay, so inside of the dereference, all we have to do is get whatever the child expression is. We don't have to know what it is. We just pop it off the stack. And then we just need to implement the dereference. So the dereference part. So now we have some memory address in Y. Again, how do we get the value of the dereference of that address? Parentheses, yeah. Good. So if we want to do the dereference, this is all it is. We just dereference whatever value we were given. We don't care how we got that value, where it came from. We just get some intermediate value from the child. This is the dereference. We'll need some other register to hold its value. And now we're done implementing this dereference. That's all we need to do dereference. And as my recommended strategy for holding intermediate values, we can just push whatever this value is onto the stack. There are other schemes for managing registers. This one is very, very simple. That's why I recommend doing it. And so this is the code that, let me actually make this bigger. So this is the code for the dereference. So now we've got all the code generated for accessing Y, for accessing the dereference of Y, and now we just need to do the assignment. And so just like before, in order to do the assignment, all we need to do is get whatever the value off the stack was into some register, and then move that into the memory address associated with X, just like we did with the first assignment, the first question. And that's it. And so these, and that's it for assignment. So assignment doesn't have any return value in our language. So in C, it would have a resulting value that could be used in another assignment or in this statement. But in our language, there's no value that's produced by assignment, and so that's it. And then together, if you do this in this post-order traversal order, you generate this code just by traversing the tree, you'll end up with a sequence of assembly that may not be the most efficient version, but is equivalent. Because we had this convention where each of the intermediate values was stored on the stack, we ensured that a straightforward single-pass traversal of this tree would generate an equivalent sequence of assembly instructions. Questions on that? Does this make a little more sense for the compiler?
Yeah.
All right, other questions on the homework? I think this is a good review of last time, dealing with pointers. And so that's part of Project 4. And then today I'd like to finish going over Project 4 and show the remaining stuff we need for Project 4. So Project 4, you'll be implementing this pointer behavior, implementing reference and dereference. You won't need to do arrays. If you want to do arrays, by all means do them, and you can get some bonus points for doing it, but you don't need to do arrays. You don't have to support typecasting because everything on every type that I've given you is just the same bit width. And so you only need to support these logic operators. You don't have to do all of the inequalities and not if you don't like. So again, bonus projects if you want to do it. They're actually they're pretty similar. And I've given this as homework, how to do less than, but it should be much simpler to only have to do some of the logic operators, and we won't test those other operators. So it's a simplified version, but by all means, do more and then get bonus points back. If you were late on your project, you'll just get those points back if you do bonus projects. So I tried to divide these up where Project 3 and 4 can be done separately. The only common thing here is the assignment statement. So assignment is where both of these from homework are implemented. So both assignment to variables and also, assignment to dereferenced variables like star y equals. That's also done in the assignment statement. All right, and then doing the project is the same as before. A lot of this is similar to before. I've given some test cases. I'll go over some of those today. And also the semantics, the rules for generating assembly. All right, so that's Project 4. I can't remember if I actually went over that in detail last time. But it's all up now and available. All right, so let's go over control flow, how control flow is handled in at least a C-like compiler. So let's first take an if statement. So what's the value of x? Oh, this is off the screen. This projector is always aligned in very new and surprising ways every time I'm in here. All right, so here's a snippet of code in simple C. We've got x equals 2, followed by an if statement, inside of which has x equals 3. So what's the value of x at the end of this program? 2? Who says 2? Other answers? Yeah? What's the condition? That's a good question. So depends on what the condition is, right? So I didn't define it here. And also when you're compiling your code, if you want to make compilation simple and you're just compiling the if statement, you can also just assume that you don't know what cond is. And the way you would generate, so how would you generate code for this? So if you don't know the value of cond when you're generating this if statement, how might you generate code for this to ensure that all possible outcomes are retained in your compiled program? Or let me ask on an if-then-else statement. Oh, okay, well. Yeah, so I guess the question is, do we generate code to assign x to 3, or do we just generate code to assign x to 2? It sounds like a trick question, but it's not a trick question. Yeah. You generate code for both. So yeah, I'm not trying to make a trick question. So in the compiler, if you don't know what cond is, you just generate both possible options, so that your resulting program will have the capacity to execute all inputs to this program. So if, say, cond is an input from the user can either give 0 or non-zero. You won't know at compile time what that input is going to be, and so you just kind of have to proactively generate code for all possible paths for this program, for all possible if branches in this program. And now the assembly language gives us ways to test values. And so the way we can, so the semantics of this is to evaluate the condition and evaluate the body only if the if condition is true. But in the compiler, we can't evaluate the condition necessarily. It may be from an input that we don't have access to. And so what we can do in the compiler is just make sure we generate both branches of if statements and generate code that will do the test for us. So this is what we want our program to do at runtime. And so we need to generate an assembly program that will do this evaluation of the condition. And assembly languages give you a way to do this, and they're called, there's lots of different variations and architectures. In the Intel world, this is done with a compare instruction, and it's a little indirect. So in the Intel world, you don't explicitly get any Boolean value in one of the sort of user-facing registers. Instead, every time you run any instruction, the machine will set flags that reveal properties of the result of the computation. So for instance, it'll tell you, is the result 0? Is the result less than 0? And you don't need to read those directly. Instead, what happens is you can generate, or you can use a conditional branch instruction. In the Intel world, these are called jumps. And so this conditional branch says jump only if the result of the previous instruction was equal to, resulted in an equal value. Really, it means branch if the result was 0. So when you took computer architecture, did they describe it this way in MIPS? Where they set flags, or not so much? So the Intel world is a little maybe unique in the way that it works. So if you think of compare as basically just a subtract instruction, then if the two values are equal and you subtract them, the result will be 0. And so compare is really just subtract without storing the result of that abstract. Instead, the flag saying whether the result was 0 or non-zero or greater than 0, less than 0, those values are stored in a hidden register silently without you having to explicitly do that. So anyway, without worrying too much about the architecture, the pattern here is to run compare on the two operands that you want to compare, that you want to see whether, they're equal, whether they're not equal, whether they're greater than 0, less than 0, and then immediately use a jump instruction corresponding to the thing you want to test. So in this case, we want to test whether whatever value we have, RAX, is equal to 0. So in the C style if statements, that would be testing whether it's false. So false is 0. And then jump if the result is 0, if it's false. Yeah.
What if we need to compare two things?
You can still do that. Let me get the documentation here to make that clear. So here we are actually comparing two things. It's just I happen to be comparing an immediate value 0.
Yeah, no, I mean what if we need to run multiple comparisons?
Oh, multiple compare statements. Yeah, we'll get to that. You have to just do multiple compares and line up the branching so that it works out correctly. I'll try to show an example of that as well when you've got, say, multiple and conditions or multiple if statements. So actually, because each, as an aside, the consequence of this is that because, and actually we'll see later, the way Boolean logic is implemented is by using this compare and branch. So have you heard of short-circuiting in C? So if you've heard of the short-circuiting rule, if you have A and B, if A is already true, it won't, so if A is already false, it won't bother evaluating B. That works because instead of actually evaluating the Boolean value of A in some register, instead it's just branch instructions. And so it can just immediately branch out of the condition as soon as it sees that A is false. But anyway, so I'm saying a lot of stuff, I'm not showing it to you. Let's build up to it. So first let's go over what the instruction set looks like. So as usual, there are lots of different variations of compare. Don't worry about what the operands are. We're only going to use a small number of them. But if you look at the description here, so the way it works is it compares the two operands and sets these E flags register accordingly. The comparison is performed by subtracting the second operand from the first and setting the static flags in the same manager of subtract. So it's basically just doing a subtract. Because if you can test whether something's 0 or not, then you can test whether they're equal by subtracting them, right? That's the kind of simplification that was used in the architecture level, just to not have to support so many operations. So you can basically reuse subtract in order to implement testing for equality. And so it says here in the rest of the specification that the condition codes that you get, whether the result was 0, are used by the branch commands, the jump commands. So if we look at jump, there are a whole mess of variations of jump. To make this simpler, I've given you the set of jump commands you need in the code. But basically, the only ones you really need are jump if equal, and if you want to do less than or greater than, jump if greater than, jump if greater than or equal to, jump if less than, jump or less than or equal to. So for this project, these are the only conditional branches you would need. And if you're not doing the relational operators less than or greater than, you really only need jump if equal. There's also a jump if not equal as well. So anyway, this is not an architecture class. I'll just sort of show you the minimum assembly you need. Whenever you're doing any kind of branching for like an if statement, you'll do a comparison and then a jump instruction, of course, for testing whether it was false or not. So for if statements, the only condition to branch on is whether, once you've evaluated the expression, the only thing you need to branch on is whether it's 0 or not 0, false or true in the C world. This is also why you can just put integers and test those in if conditionals, even though in some kind of mathematical sense, if statements are a Boolean check, whereas in C, you can just pass in any old integer or a pointer or anything. And as long as it's non-zero, it's true, and whenever it's 0, it's false. So this is kind of the consequence of the architecture, where the architecture can quickly check whether something is 0 or not through this comparison instruction, and then branch if it's 0 or non-zero. So kind of a crash course on the architecture, but questions on that? So basically, as long as you have a way to test for 0 and branch on it, you can implement if statements in your language. Okay, so let's look at this. Oh, that's a while loop. So this code can be thought of as, well, actually, let me actually write kind of informally what the assembly would look like in this case. So to kind of put some pseudo-assembly here, we'd have an assignment to X, and then we'd have a test of whatever cond is to 0. And if it's equal to 0, then do we execute the body or do we not execute the body? So if it's equal to 0, yeah.
If it is equal to 0, then yes. Right?
It's confusing, right? So this is going to be the trickiest part of doing this. So in C, what does cond have to be in order to run x equals 3? Yeah. Non-zero, yeah, non-zero. So now you can choose to design how you generate the code however you like. I'm going to generate this in such a way that the if branch comes first in the assembly code and the else branch comes next. And so the way I'm going to do that is I'm going to invert the test. Instead of testing whether it's true, I'm going to test whether it's false, because these branch instructions, they branch whenever the condition you made was satisfied. So if I test for false, I'm only going to jump. Well, I could also use jump not equal. There's a billion ways that you could write this code. The way I'm showing you to write it is to test whether it's false, and then branch to the else branch label if that condition is met. So the way branches work, or jumps in the Intel assembly work, is you can put a memory address to jump to in your code, but in the assembler we can just use a label for that. We can use a string label. So I'm going to make a new string label called else branch, and then execute whatever the else branch is. In this case, there is no else branch, so just be the rest of the program. And so if the else branch isn't taken, that is, if the condition was not false, that means the condition was true. And so I don't branch. And if I don't branch, I just run whatever the body of the if branch was. And so if this were an if-then-else statement, which I'll show later, I would have to skip the else branch. In this case, the else branch and the if branch are the same. So this looks, again, like silly code to just jump to whatever the exit label is. But the main point I want to get across here is that we need to do a test that will check whether we want to go to the if branch or the else branch. Here I'm testing whether we want to go to the else branch or not, or whether we want to skip the if branch. And so if that test fails, we don't take the jump, and instead we just continue running whatever the if branch was. Questions about this? So this is going to be some sort of like tedious, mind-bending logic stuff you have to do in your head when you're generating this. But if you could just follow my scheme that I think I put in the project for doing this, yeah.
So how does it? So if the else branch is after it, right? So
Yeah.
how does it not execute whatever code is in the else?
Yeah, so I probably should, I think I'm skipping ahead to the else thing. Let me make this. Let me simplify this. I'll get to the if then else statement. So I probably should have just made this end, like the end label. Let me show the if then else in a second. So this is whatever content is after the if statement. So this is how you could, one way to generate code for just an if statement, So just to review, we run whatever's before the if statement. We check whether the condition is false. If it's false, we skip the if statement. If it's true, we don't do the jump, and then we run whatever the if statement is. Sorry, I was skipping ahead a little bit to the if then else statement. Yeah. No, it's I want to build up to it. All right, questions on this code. So in this case, we kind of need to have a jump whenever it's false, because we want to skip, if it's false, we don't want to run the body of the if statement. Yeah.
Wouldn't we still want to jump to the end after we sign x equals 3, like if we want to continue our code?
You could, but strictly speaking, as long as we generate the remainder of the code directly after the if statement, then the program counter will just be incremented by 1. And so that'll be so there are, in a real compiler, the way these kind of blocks and if statements, they're handled a little bit more cleverly. In our compiler, if we're just doing a single pass, the very next code we generate will be the next thing in the tree, the next thing after the if statement. So it'll just happen to follow, if that makes sense. So we could, and in fact, when we go to see the else branch case, you will need to do that to avoid running the else branch. So questions on this? Okay, so let's look at an if then else statement. Okay, let's say we've got we have cond again, and we've got let's do it this way. Okay, so just to review the semantics of this, what's the value of x? Let's say I print x here. Let's set x to 1 up here. So what's the result of running this program? Say cond is read from the user. What's the result of running this program? Okay, so yeah, what are all the possible outputs of this program?
X is going to be 2 if the condition is true. X is 2 if the condition is true, or else it's going to be x is going to be 3 if the condition is false.
Okay, good. So x is going to be 2 if the condition is true. X is going to be 3 if the condition is false. Are there any other possible outputs of this program? Could x ever be 1 printed out? No, right? That's the behavior of an if statement. Okay, so let's see how we could generate this in assembly, or how we could emulate this behavior in assembly. So we do the assignment of x equals 1, because we don't want to have to look ahead in our code in order to figure out whether x equals 1 is dead code. And then just like before, we compare cond to 0. So now this is saying cond is false. So the way we want to do this is we can set up, you can think of this as setting up two targets of a jump. So we either run this code or we run this code. So let's make a label for else. And just like before, we don't actually need a label for if. We could say, jump if, and then immediately have a label for if. But just like before, if cond is true, then this branch will not happen, and we'll just run the if statement. But if cond is false, then the branch will be taken, and we'll execute the else branch. Now, the problem here was already foreshadowed by you guys. The problem here is that if this is the only thing we do, then what's the output of this? What's the output of this program? So if my next statement is print X, what's the output of this assembly program? Yeah.
X is 3.
Yeah, X is always 3 in this program. So let's go through why that is. So if cond is 0, then we take the branch, we skip X equals 2, and we go to this label here and run X equals 3, and print out X equals 3. But that's what we expected. That's what we expected in the behavior of this program. But let's see what happens when cond is true. If cond is true, this comparison is not 0, it fails. The branch is not taken. And we assign X to 2, just like we're supposed to do in our program. The problem is that the next instruction in this program is X equals 3. So then we assign X equals 3 and we print out X equals 3. So this assembly code, while it's valid assembly code, is not equivalent in terms of its input and output to our C program, or our simple C program that we want to generate. So what's the resolution that I think you came up with? You put a jump, so you put an unconditional jump to skip over the else branch. And so we can just make a label just like we had in our if statement. We have a label to jump to the next instruction after the if statement. And so as soon as we execute our if statement, we don't want to execute our else statement because it's the next sequence of instructions. So we may use another branch in order to skip past our else statement. And just like before, you could conceptually think that there's a jump end here as well, if you want to be kind of completionist about this. So the structure of this, the kind of template here, well, let me actually put the circle here. So there's kind of a template here that we can think of. So we don't need this jump end. I'm not going to put the jump end. This is our template for an if statement. Oops. This print X is also not here. That's a statement afterwards. So you can think of this as a template for generating any if-then-else statement. Just like with generating expressions, you don't really care what's inside the if branch and the else branch. You don't have to know what this is at all. You can generate those separately from the if statement, or while you're generating the if statement. And you don't care what comes before or after. So this is the template for generating an if-then-else statement. And notice that the last thing you generate in the if-then-else statement is an end label. You don't even generate any code, you just generate a label. And this is a little weird in assembly. If you just ran this assembly program, I don't know if it would work just by itself. You would need some final instruction here. You label instructions. But the resulting label that you generate from the if statement gets effectively combined with whatever the next statement in your program is. So whatever print X is, whatever that gets generated. Questions on that? So that's the pattern. Actually implementing this is a little trickier, because if you want this assembly code to be generated in sequence, you have to first start generating part of the if statement and then call the code generator for the if body. Generate more from the if statement and then generate the code for the else body. So in other words, to see what this looks like in a tree structure, if I've got an if-then-else statement, it's got code, it's got some expression here. It has some statement for its if body, and it has another statement for the else. So when you're generating code, unlike expressions, you can't just do purely post-order where you generate both. I mean, you could if you save their outputs. But in the compiler design I gave you, generating code for the statement will just spit out print statements. So the way this works is you call the code generator for the expression, and then spit out code for the comparison, spit out the jump to some new label, and then you call the code generator for the first statement. And after that, you need to generate, once you're back in the parent, you need to generate code for the end label, generate the actual label. This should be the else label. And then generate code for the second statement and generate the end label. Okay, that's a very rough schematic. It's listed out in your code. So let me do an actual example to show you what this looks like. So let's say expression is cond, statement is x equals 2. The statement is x equals 3. Then when you go to compile this, when you call CodeGen, you'll first need to call the code generator for expression. So this is the code generated for expression. And who cares what it does? You already have a code generated for expression. You just know at the end of it, it's going to push RAX at the end of it. So then once you're back inside of the if statement, you can generate your comparison. Or actually, you would have to pop RAX first. And then generate code to check whether it's false. And then jump to whatever the else branch is, whatever the else branch label is. Now, because there may be multiple if statements in your language, you'll need to generate fresh labels, but I'll talk about that in a second. There's functionality I've given you to do that. So you need to jump to some new label. And then once you've generated this header, the code to test the expression, then you'll generate whatever the code is for the if statement. So you generate code for this if statement here. Once that code generation is done, you'll have all the code for the statement. So you'll need that unconditional branch to the end of the entire if then else statement. And once you have that, you'll take whatever label you have for the else branch, generate that, and then call the code generator for the else branch. And it doesn't matter how that code is generated. It doesn't affect how you generate code for the if statement. And once that's done, you just generate the end label, whatever new label you created for that. And that is all the code you need to generate for an if-then-else statement. It's really only, 4 instructions for the if statement. But they're organized in such a way that the nested statements are sequenced so that the logic of this comparison and jump works out to be a program that's equivalent to the behavior of our C if-then-else statement. Questions on that? So whenever you see this box and red arrow, you can think of this as a recursive call to CodeGen. So this would be CodeGen expression. This would be code gen statement, code gen statement. So this gives you a pretty clear sequence of code in your compiler. You would call pop, or you would call the code generator for the expression, call pop to emit a pop instruction, call compare to emit a compare instruction, and then make a new label. So new labels in our code generator are very simple. They're just a counter that always increases. So you just increase the jump label counter, call the label, just increase that counter and call the generator for jump to go to that counter. And then call code generator for the if statement to make sure that its code is generated in the right spot in your if then else statement. Once that's done and you're back inside of the generator for the if then else statement, you generate your jump label with a fresh label, generate the actual label, and there's a macro for doing this, generate the actual label for the else branch, and then recursively call code gen statement for the else branch. Finally, you make your end label, and voila. I know it doesn't sound easy, but hopefully this schema shows you that it's really just a template. The compiler will generate the exact same instructions every time it runs an if statement. The only thing that are variable are the nested calls to its children and the fresh labels that you make for this if then else statement. But otherwise the template is the same every time you generate an if then else statement. Questions on this? Yeah.
So, do we only consider 0 to be false?
Yes. Yeah. Only 0 is false in this language.
If you wanted, like a select it, you just check if it's less than 1.
No, in C, less than 1 is still true, I think. I think in C, it's only 0 is false, if I'm not mistaken. I think. What's that? I don't think so. I think, test it out. Test it out. What's that? Negatives are true? Yeah, I think it's only 0. And I think this is effectively why. Or this is kind of what it comes from. It comes from the, this choice comes from here. But test it out and see if you get something different. All right, questions on the if then else statement generator? So this should also be laid out in the project description. Oh, it's laid out in the lecture notes for this. So it'll show you the template for if then else somewhere in here. Okay. All good? Questions? Any other questions on if then else? Let's do one more control flow construct. We have another control flow construct in our language, and that's the while statement. All right, so what does this program do? So what's the behavior of this program? What's the result of running this? Let's say we printed out CNT counter. What would be the result of this program? Go ahead.
Well, nothing's printed out. It'll just ultimately count will be, I think, 0 at the very end.
So who says count will be 0 at the end of this program? Or says something else, it won't be 0, it'll be something else. So let's walk through this program using the semantics of C. So if count is 3, and then we call while count, is the condition true or false? in a C-like language? Count is 3. Who says true? True, right? So it's true. So it'll enter the body of the loop, and it'll reassign count to be count minus 1, which is now 2. And then the behavior of a C while statement is to go back and reevaluate the condition. You reevaluate the condition, count is now 2. Is it true? It's true, right? So then we evaluate the body again. We get count equals 2 minus 1, we get 1. The behavior of a C while loop is to reevaluate the entire condition. Its count is now 1. Now count is assigned to be 1 minus 1, which is 0. We reevaluate the condition. Now count is 0. What happens? The loop exits, right? The loop exits. So it's just like an if statement. If whatever is 0, 0 is false for conditions in C. So what happens when when the condition is false? Doesn't do anything. We don't evaluate the body. We skip past it and continue executing whatever the remaining instructions are. So the result for count in this loop is 0. Count will be 0. So let's look at this behavior in another way in C. So I call this a kind of desugared version. You could just eliminate while loops in C if you wanted, and replace them with a goto. And so one way to think of a while loop is really just an if statement that has an unconditional branch to go back and reevaluate the if statement. So take a look at this for 1 second. But if you take out the head and the goto head, this is just an if statement and works just like the if statement we saw before. But here, instead, we added a label so that we could rerun this if statement over and over and over again. And we added this goto so that whenever we had a true condition, whenever we evaluated the if statement, we just always reran the entire if statement. Kind of makes sense? Have you ever seen this before? Who's seen this before? And you can do the same thing with for loops. You can desugar a for loop into a while loop and then desugar that into an if statement with a branch. Okay, so if I've convinced you that this is equivalent to a while loop, how can we generate an equivalent assembly program, or how can we write an assembly program that behaves equivalently to now a while loop? Or do you have suggestions about how we could translate this into assembly? Yeah. Yeah. Oh, well, yeah. So, so the key here is that you would generate code exactly the same way you would generate for an if statement, but then just add this additional unconditional branch to the top of the loop, to the top of the condition generator. So diagrammatically, if we've got this while loop, that's off the screen. So if we've got this while loop here, then we can generate the code just like we would with an if statement. And so the way that would work is we take our condition, which in this case is CNT, compare it to 0, and then jump to whatever the end of this, whatever the code is that comes after the if statement, if we think of this just as an if statement. And inside here, we put the body of our while loop. In this case, the body is count equals count minus 1. And so this is the exact code that we had for an if statement, right? If we go back and look at an if statement somewhere, it's identical. It's compare and then jump past the if statement if that comparison turns out to be false, if the condition is false. So it's the same structure as an if statement. But there's one key difference. And so how can we modify this template for an if statement so that it behaves like a while loop. Yeah. Okay, so where do we jump? Where do we put the jump statement? And where do we put the label? Okay. So we have an unconditional jump here. Let's call it head of the loop. And where do we put the label for head? Yeah, good. That's it. That's the only difference between an if statement and a while loop. It's just an if statement that has an unconditional branch inside of its body back to the top of the statement. So if you can generate code for an if statement, you can generate code for a while statement. Very similarly. This also kind of reveals a little insight in about what programming languages are. Because the fact that we can translate this language that has a lot more statements than the assembly into assembly kind of reveals something about languages, about their expressive power. So even with this simple set of instructions that, there's no while loops, there's no if statements, there's no for statements, we can still create an equivalent program even in this simpler language. This is sometimes called desugaring, where you take the syntactic constructs that are more complicated in one language and you represent them in a lower language, or compilation or translation is another way to say that. Questions on this? Questions on the while loop? Yeah.
Do we create our own labels, like our own names for the labels, or is there
Yes. Yeah. I've given you some functionality to make it a little easier to deal with labels. But the main thing is, if you have multiple while loops in your program, they need to have unique labels. So in the assembly language, you have to have unique labels for every position that you want to be able to branch to, because otherwise, the assembler wouldn't know which address to put for that label. So the simple way to do it is to, whenever you have to generate a while loop or an if statement or anything with branching, you just first create some fresh labels for yourself, some fresh unique names. And a very simple way to create fresh unique names is to just have a counter that always increases. I mean, as long as the counter is big enough for all of your labels. And so whenever you generate a fresh label, just increment your counter and then concatenate it with some like label L1 or something. So I've given you code to help do this. Let me show this code. So I've given you these branch instructions, all the different variations, and I've given you a label macro. And so the label will just concatenate whatever number you give it with .l. It's just a convention. There's no kind of truth to it. And then I've also given you this label counter, which is somewhere. Oh, I thought I gave you the label counter. So you can just maintain a global counter. I think I must have not put the counter in there. So I didn't give it to you, but you can just create a global counter, and there's the code for the if statement if you want to use that, which I just put up here. So yeah, you just use you just have a global counter. So you just maintain a global counter. That's it, and then and that's how you generate. That's like the classic way to generate fresh names if you have your own namespace. But other than that, that's the only variation you need. And then for any of these, like I said before, for any of the nested constructs like the bodies, you just recursively call codegen statement, because if statement doesn't care what's in its body. You just generate whatever it generates. As long as it's correct, then the composition of it with the if statement will be correct. Yeah.
What you were saying earlier about the whole seat assembly, the
Church Turing thesis. Yeah, well, that's an even bigger one. From what I understand, so this is not my area, but the Church Turing thesis is that this is what computability is. This is what computable numbers are. The consequence of that work is that so both Church and Turing were trying to define the kind of essence of what computability was, like what all computable numbers were. And they came up with two different languages for describing computation, the lambda calculus and Turing machines. And later researchers proved that they are equivalently powerful. That is, if you can program one thing in lambda calculus, you can implement that same thing in Turing, and vice versa. So yeah, it's definitely tied up with that Church-Turing hypothesis. But it's supposed to be it's almost a definition of what computability is. I don't know if there's a way to prove that thesis is true, but it's taken as a given that this is that this is the limits of computability currently. But yeah, good question. Take a computational complexity class. I think that'll learn, or theory of computation with others here who are better at that than I am. Other questions on this? Okay, so that's, I think, all of the control flow constructs in simple C. There's no for loops. If you want to implement for loops, it can be a bonus project. It has a similar kind of desugaring behavior. So maybe we can actually go over it quickly here. If we have, say, a for loop, let's just say I equals 0, I less than n, I plus plus. How could we represent this how could we translate this to simple C? Let's start there. How could we take a C style for loop and rewrite it in simple C? So simple C doesn't have a for loop, but how could we make a program that does the same thing as this? I mean, besides just saying x equals n or something, that actually has the same, yeah.
You can convert that into a while loop.
Okay, so what would that while loop look like?
First, we have to assign a variable to 0 outside.
Okay, so I, right? I. So let's translate this exact program. We have to do all. Let's translate this program. Okay, and then what would we have?
And while
Okay.
I is less than n,
Okay.
inside of it, you x plus
Okay.
and increment I by 1.
Other views? Other options? Does this look good? Does this seem equivalent? So this is exactly the semantics. You can define the behavior of a for loop in terms of a while loop by just, you can almost do this very syntactically. You can just literally cut the initializer out, put it on its own statement, cut the condition out, make it the condition of the while loop, and then cut the incrementer out and make it the last line of the while loop. And voila, you've got a translation of a for loop into a while loop. And since we now know how to do a while loop in our language, should be able to convert this into assembly code. Could actually add this to the grammar, could make a grammar for this syntax. And then when you're traversing your code generator, you could generate the equivalent assembly code directly from this for loop in simple C. So that's another possible bonus project you could try. That one's kind of more fun because you can actually add syntax and then actually add a code generator to generate new code and then see your new language construct working. All right, questions on control flow? So yeah, I have some tips here. So, always keep in mind that we're not trying to evaluate the code we're bringing in. We're trying to translate it to assembly. So we need it to work for all possible. We need it to work the same way, which means in the compiler world, that means all inputs give you the same output for a deterministic program. When you need fresh labels, just use a counter. And so as I showed, the if statement doesn't actually generate the code for the bodies of the if and else branches. You just recursively call, or the condition, you just recursively call the code generators for those. Okay, so let's go over Boolean operators. Boolean operators in C, because of the short-circuiting behavior, are a little tricky. But if you understand if statements, it's a little easier. So just like with for loops and while loops and if statements, we can represent a Boolean conjunction, a Boolean and, using if statements. So you can think of Boolean and as just nested if statements. So if this is the body that I'm trying to execute, then look at it this way. So if we just built the truth table for this and we said, all right, well, so under what settings of A and B should the body be executed in this program? So if the body is, print hello world, for what values of A and B should we print hello world? True, yeah, good, yeah. So what about true, false? No, it won't work. So only when true and true, both A and B are true. And so you can see that this is equivalent to that. So if A is false, the body won't be executed. If B is false. If A is true, but the B is false, body won't be executed. The only time body will be executed is if both A and B are true. So this strategy actually shows us how we can generate Boolean and with short-circuiting in our language. We can just basically we know how to do if statements, so we can just combine together two if statements in order to implement Boolean and. Make sense? Actually doing it is a little trickier because we have to track all of our labels, and we have to kind of make nested if statements together. Okay, so it's really annoying to work this out. I'm going to try to do it. I'm going to try to work this out together so you can see that it's not that fun to do. It's kind of tricky to do. All right. So let's have our guide here. And then let's just make our body x equals 1. Okay, so how do we generate an if statement testing if A is true? Well, just like before, we have a comparison to check whether it's false. And so if it's false, we want to branch to the end, wherever that is. So we're going to branch out of it. If it's true, then we want to test B. So we want to have this nested if statement, although in assembly there's no nested constructs, but we want to, if A is true, we'll continue to the next statement and we'll test whether B is true. If it's not true, we'll jump to the end. But if it is true, then finally we can execute the body. And now I think at this point we can just, so we can just branch to the end. So this is kind of loosely what the structure will look like of this nested if statement. Make sense? Questions on this? Okay, so the problem is this this conditional might be combined with other expressions like or C, then another and, it might be some nested structure here. So we can't just directly, unless we want to do some very complicated translation of this to a series of if statements, it'll be much easier for us if we turn this into a single value, a true-false value, instead of actually generating code that will run the body. So the way conjunction is going to work is we're going to use this same structure here, but instead of trying to think about how we execute the body, we're just going to use this to generate either true or false from the result of our Boolean operations. So that's why this code looks the way it does. So what we're going to do is we're going to have an if branch here that will generate true for the result. Otherwise, there'll be a kind of single else branch that'll generate false for that code. So this is why this code looks the way it does. We have extra branches here. All right, so let me try to work this out, if I can. Let me leave this out. So the code we want to have is, if this is true, then set the result to 1. Otherwise, set the result to 0. So result here is going to be the value of this expression, so that we can then use it in our if statement. So we're not actually going to literally combine the evaluation of this expression with an if statement. Instead, we're going to evaluate this expression by itself, preserving our tree structure. So we're going to use this same strategy of testing whether either of these is false. But let's make a label called false to remind ourselves that when we jump to this label, we want to set the result of this computation to be false. So I'll just like we do with all of our expression generators, I'll use RAX for temporary variables. And so if at any point I determine that my conjunction is false, then I will jump to this block here that will set the result. I'll store the result in RAX. I'll set it to 0 to record the fact that the entire expression is false. So what's going to happen here is later, the next thing that we'll do is push this result onto the stack. So this whole computation will give us the result of the tree A and B tree. So this will be because A and B is an expression tree. So to fit in with our expression tree evaluation scheme, we'll always push the result of this computation onto the stack, onto the top of the stack. Questions on this? Does this make sense? Sort of? So this is the code that'll be generated when you evaluate logical AND. Okay, so this should be A. So when I compare 0 to A, if it's false, then I want to set the result of the whole expression to be false. And I do that by basically pushing 0 onto the stack. I save 0 on the stack. Yeah?
Does it matter if it's A or B?
Actually, in the C world, so with short circuiting in C, they evaluate A first and then B. So it would make a difference which one gets evaluated. In our language, we don't have side effects. That is, in C, B could be like an assignment that will update some value. So in C, if this, so let me give an example of this. So in C, if I had 0 and x equals 1, this assignment would never happen in C. If this were 1, the assignment would happen. So put it another way, if I had x and x equals 1, if x is 0, x is going to stay 0. It's not going to be reassigned. If x is anything but 0, it'll be reassigned to 1 in C. Now in our language, we don't have these side effects, so it actually wouldn't matter. Basically, it's associative in our language to do this. So it actually wouldn't matter. It even wouldn't matter if you didn't do short circuiting. So you could, generate the code to compare A, both, and then compare both. Yeah.
Could you have a function call that changes a global?
Yeah, that's true. You could. Yeah. Okay. So we do have side effects in our language. The version I'm having you implement doesn't, you don't use globals, but you're right. Because we have globals, yeah, there would be side effects. You're right. So it would matter. But I didn't specify the short-circuiting behavior at all, so it actually doesn't matter. You can do it however you like. In C, though, yeah, be aware that short-circuiting does actually affect side effects and assignment because of the complexity of C. Okay, so we've tested whether A is true. If it's not true, then we want the rest of the expression, the whole expression, to be 0. So this is how we take 0 and push it onto the stack to hold that intermediate value. If it's true, then we need to make sure that B is also true. If it's not, then we can just use the same label we created to set the result of the expression to 0. There are lots of different ways to generate this code. This is the way, I did it. So if we finally pass through all of these two gauntlets, we can then finally record true as the result of this expression. So is this done? Are we done here? Why not?
Because it's still got the false in the next two lines.
Yeah, so if we just left it the way it was, then we would, just like with an if statement, if an else statement, we'd run effectively the else branch. So we need to skip our else branch here and just go to the end of this expression. So there are lots of different ways to write code that's equivalent to this A and B expression. This is one way to do it. So it's effectively an if-then-else statement where we just have two comparisons. Questions on this? So so now this is not actually valid assembly yet because we've got A and B here. A and B, this is not a valid Intel syntax. But so first of all, where do we get the values of A and B from in this tree? So A and B are some expressions. How do we get the values of those? What was that? From the stack, yeah, exactly right. And so how do we make sure that the stack is populated with the intermediate values? So you're right that we pop from the stack. So let me... So we need to get these values from the stack in our scheme. So I'm going to just use RAX and RBX for these values. And so we'll pop those from the stack. Let me remember the ordering here. First in, last out. So we're going to pop these from the stack. But how will we generate code to ensure that the values of A and B are actually on the stack at runtime? Or how do we generate code for A and B? Yeah, exactly. So you'll call CodeGen on whatever the left child is of this AND statement, and you'll call CodeGen on the right child, and that will guarantee at runtime that the stack holds first the left operand, then the right operand. Questions on that? Does that make sense? And then once you have that guarantee, you can just generate this code always for conjunction. You always generate pop statements to get those operands off. You always do two compares. If either of those comparisons end up being false, then you set the result of the expression to be 0. Otherwise, if neither of those branches happen, that is A and B are both not false, then you set the result to 1. Questions on this? So it's really tedious to work through this. It's like, you know, you have to like keep in mind the true-false thing, and then they get inverted. And you can feel free to come up with your own scheme for generating this. This is not necessarily I don't know if this is necessarily the best way to do it. The real compilers will often invert the condition for this very reason, to have the if statement generated first. But yeah, in the version of Simple C I'm asking you to implement, there aren't side effects, although be aware, as your fellow student pointed out, we do have side effects in the full language. Okay, questions on this? So let's rack our brains a little more and think about how would you do disjunction? How would you do or in this scheme? I can't even remember how to do it. Yeah, go ahead.
I was gonna say like two if statements, but like if you're like adding like two not nested if statements, but then like you run into the issue of like if you're adding something, we would add it twice. So like
you could use two if statements again. We used it before. Or
you could do two if statements, and then like in the first if statement have like a jump, like unconditional jump that just goes.
right, yeah, you could have, yeah, that's right. So I think what you're saying is, yeah, you have two if statements that. So okay, so I guess first of all, stepping back, what is the behavior of or? So with and, if it's ever zero, either one of them, you just immediately set the whole expression to zero. The whole expression to zero. That's the short circuit behavior. That's what we just did. For or, it doesn't work like that, right? So if one of them is zero, then the other one, you still have to evaluate the other one, right? But what's the kind of rule for, or what's the simplification for or? If any, well, yeah. So one way to say it, if either of them are true. Also, if either of them are true, then you immediately set the whole thing to true. It's actually it's the inverse of what we just did. And this is that what's the rule in logic? Like the negation of an or. Right? Is there a name for this rule? I can't remember. So if I have A or B and I negate it, what's one thing that this is equivalent to? De Morgan's law, yeah, De Morgan's law, right? So this is equivalent to saying A and not B. So one thing you could do is you could like invert these. You could implement not, and you could invert them and then just use the same template for conjunction. It's one way to do it. Or you could use the scheme that your fellow student pointed out, which is I think what I did, which is to check whether, okay, yeah, so I think this is what you were saying, right? So have an unconditional check, an unconditional branch, to always do the sort of, right? So what you're saying. This is two if statements where no matter which one is true, you always execute the body. This is probably a little weird. This is weird. You might not want to write this in C. But it's the same idea, the same spirit of what your fellow student said. So you could do it this way, where you effectively have two if branches, and whenever either of them is true, you branch to something that will set the result to true. So let's see how I did it. I don't remember how I wrote this. So let's see. Okay. So I use jump not equal to implement this. So so this is saying if the left operand is false, if it's false, then, now I'm confusing myself. Yeah, so this is saying if this is not false, so compare it to zero. If it's not zero, that means if it's not false, which my comments say, fortunately. So if it's not false, then we branch to set it to 1. So I think the way I designed this was to be basically the same as our conjunction. Where's our conjunction? So our conjunction has this same structure where we check, is either of them false? If either of them is false, then go to this single statement that assigns it to false, the result. Otherwise, assign it to 1. I just inverted the logic of that by saying if either of them is true, then branch to this one spot that'll set the whole result to be true. But if we pass through both those gauntlets, if we can't show that either of them is true, that means both of them is false, then we set the result to 0. So working this out in your head is a little tedious. As you can see, I'm also confusing myself as well. You can also kind of use De Morgan's law to convince yourself on paper that this works. And this is effectively De Morgan's law, actually, I think, because we're changing the comparisons from equal to not equal, and then we're changing the resulting value, or negating the resulting value. So this is actually De Morgan's law, I think, right? So we take whatever this resulting value is, and we negate it, and that will give us A or B. So this C here, this is the result of not A or B. So if we negate it, then we get A or B. To negate this, let's write this in a different color. So if we turn this into 0, and we turn this into 1, that's the negation of this A and B, right? We just swap its output value. If its output value is either 1 or 0, if we swap that value, if we invert that value 0 or 1, this gives us OR. So OR is in green. And then in order to negate the tests, so in order to negate, have not A instead of A, we swap this out with jump not equal. That's the inversion of jump equal. So this is my glib way of showing you how you can implement OR using the same code that you use for AND. You just negate the tests and then negate the output. So it's the same thing. Another way to say this is if I do double negation on A or B. So this should be true, right? If I do double negation on A or B, I should just get A or B, right? I think in Boolean logic. So if I wanted to be really clever, I could point out that before I even get here, I can use De Morgan's law here to say, well, okay, this is the same thing as saying not A and not B. So what I can do is I can implement the negation of not A and the negation of not B by just swapping jump equals the test for false with the test for true. So that'll be the same thing as saying not A. And I can negate the result by just swapping 0 and 1, by making the result of the expression 0 when it would have been 1 for and 1 for when it would have been 0 for AND. So I don't know. So that's 7 different ways to think about this. But it's probably instructive to sit down and kind of work out yourself. Just take a test program and work out the assembly code. Or you can just look at my template here. So there's a template here for doing this. The indenting is not desirable, but so here's conjunction, here's disjunction. So if you want to work it out yourself, work it out on paper, but I have example code here for doing it. Okay, so I know that's a little mind-bending and it's kind of tedious bit-twiddling stuff, but questions on disjunction and conjunction? I think when you go to actually write it and work it out and see your test cases, so I strongly recommend having simple tests. I think I gave you some tests, but make sure you look at the assembly code and work out an example before trying to just write the code, because the code will be written for all possible inputs and it has to work together with the rest of your compiler. But use simple examples. That's my reminder. So here's some. Short circuiting, as we talked about, C would not actually evaluate the right hand side of the conjunction. I haven't given you a specification of this in our language, so don't worry about getting that part correct. So in this scheme, how would negation work? What would negation look like in assembly? Yeah.
Change anything non-zero to zero and zero to one.
And how would you do that in assembly? So there's a little hint here. We kind of do it here. So if you just had one operand, and you can just check, oh, hey, is it false? If it's false, then set it to true. Otherwise, set the result to false. So it's just one. It's basically an if statement. It's just an if statement that says, if A, then the result is not A, or the result is 0, else the result is false. So this is not required for the project, as I wrote in the description, but implement this for bonus points if you want to implement any of these other operators. And relational operators, I gave you that as a homework exercise. We can go over it next time. It's similarly it's a similar vein of doing all of this, but this is the kind of desugared version of negation. And you can implement that in assembly similarly. Yeah. I'm pretty sure it's not required. Let me double check. Only needs support for, oh no, sorry, it is required. Sorry. Wait, only needs support for, oh no. Wait, only needs support for A or not. Oh, sorry, no, I am requiring all of these. Sorry about that. Not is negation. Well, yeah, is Boolean negation. Okay, so I said in the beginning of the class that these were not required. So let me actually take those out as a requirement. I'll remove that as a requirement. Negation is pretty easy. So do negation. Negation is easy. But these I'll leave as a bonus exercise. I'll update this to do that because I said it at the beginning, so I don't want to switch like that. So try not. Not is very simple. If you can do and, not is very simple. But these are a little more painful. So I'll leave those as a bonus exercise and change this. If I forget, let me know. Otherwise, that should be everything you need, I think, for Project 4. But as usual, ask questions on EdSTEM, come to office hours. We'll go over the homework next time. Questions? Yeah. Yeah, it's extra credit. It's extra credit. So there's an additional bonus category that I've added. I got to remember how this works. Remind me, or send me an email because I got to make sure this is set up correctly. The way it works in web courses is a little confusing. You have to make more points than there are available or something like that, or you have to make all the other you may have to make the categories add up to more than 100%. And either I didn't set up correctly or web courses is not computing it correctly without all of the assignments being turned in. But actually computing your grade is actually very easy in the way I set up the syllabus. You just add up the number of points. So 1 point is 1%. So if you just add up the points you have and divide it by the points available so far, that's your score so far. So I designed the point system that way. So actually, I think to avoid the web courses stuff because I couldn't understand how it was computing partial scores. But you know exactly what percentage you have so far out of the percentage that's been assigned so far. Other questions? All right, so thanks all for bearing with me without a break, and we'll go back to normal next time. I have been recording, fortunately, and